So guys, it's 9:38 on a Friday night, and as things look at the moment, I'm going to be the last thing in between you and the bar. And,
you have a full room of people.
I do feel bad about it, but I promise I'll give my best that I don't have Manfred to stand up and give me this scary look. So I'll really try to do it right. And so the story tonight is on the left-hand side of the slide. You see a snapshot of the Jena Bioscience website, the landing page for crystallography. So it's kind of like a schematic sketch of the workflow of a crystallographic experiment. And during the past HEC meetings, we have spent quite some time on talking about the earlier stages of crystal screening and crystal optimization and hit optimization and protein engineering and protein surface modification and this kind of stuff. And tonight we just decided to give you a short overview about the reagents that we have for phasing. It's the very last hurdle in the whole process, and most of you probably think that molecular replacement is the ultimate method for phasing, which is true. But when you go into the PDB database and actually look what percentage of structures have been solved with molecular replacement, you see that only about 60% of the structures of all time were solved by molecular replacement. And even if you look at the younger structures since 2011, you see that still 20 or 21% of the structures have to be solved by experimental phasing. And this is what this talk is going to be about. It's about the second line of defense, the experimental phasing, the MIR and series and MAD and SAD business. And I'm going to talk about three things: the tantalum and the tungsten clusters for protein derivatization, the magic triangle, and the heavy atom containing nucleotides and oligonucleotides. So, first of all, the clusters. They're molecular arrangements. You can see the pictures on the left. The tungstate cluster consists of 12 tungsten atoms that are rich by oxygens. Those forming together kind of like a super heavy atom. And you can use the shell of the tungsten for anomalous scattering, for SAD, and for MAD phasing. They're highly soluble in water. They're also available in three types of charges, so different modifications of the clusters. So with the resulting overall charge of -3, -6, or -10, so you can use them for screening and finding out the optimal binding to your particular protein of interest. The second example I want to briefly show you is the tantalum bromide cluster. It's a similar arrangement. So there are 6 tantalum atoms clustered by 12 bromines. Again, this arrangement forms kind of like a super heavy atom, and tantalum as well as the bromide are both anomalous scatterers. It is also soluble in aqueous solutions, although not as well as the tungstate clusters, but it's stable over a large pH range, and both of those are suitable for in-house sources. So the second example is the magic triangle. It's this structure. So the chemical name 5-amino 2,4,6-triiodoisophthalic acid. I think the term magic triangle is a bit snappy. That's why we decided to use that for the marketing. So what you can see here, it's three iodine atoms. There we go. 1, 2, 3. And they are accompanied by 2 carboxyl groups and 1 amino group. So you have negative charges here, and you have a positive charge here, and the iodines, they contribute in hydrogen bonding. So you can really get a high occupancy in protein binding because you have so many functional groups that can interact with your protein of interest. So it's easy to get it somewhere into the crystal. And also, once it is into crystal, it's such a unique structure, this equilateral triangle, it is very easy to identify on the density line.
Again, the iodine allows you to use in-house sources, so you can save some money on travel costs. You don't have to go to the synchrotron necessarily. The last example for tonight would be heavy atom-containing nucleotides and oligonucleotides. First, I give you some example for single nucleotides. In the upper picture, you can see an ATP derivative. It's actually not really ATP. You may realize there is the amide group in between the beta and the gamma phosphate, so that prevents the phosphate group from hydrolysis, so it's a stable analogon that can be used for crystallography. And you find either at the 2' position of the ribose or at the 8 position of the base, you can have a substitution which can either be a bromine, an iodine, or a selenium group. And of course, the method is limited to enzymes that do bind ATP, but it's actually quite a few enzymes actually that do bind ATP. I'll just give you some examples here. So we're talking about all the kinases, the motor proteins, the chaperones, and many more. Second version is the GTP. Similar idea, non-hydrolyzable analog, substitution either at the 2' or the 8 position. Again, it can be used for GTP binding proteins, which is the majority of the proteins involved in signal transduction of the G protein cycles. So the 2' substitution has been shown to work for proteins such as P21-RAS or RAD5, so the RAS type GTPases. And again, a similar approach for UTP and CTP. This time we used the pyrimidine 5' position for the substitution. And here you can apply bromine, iodine, or mercury derivative. And this can be used for polymerases or nucleotidyl transferases. Again, as I said, the method is limited to NTP, so nucleoside triphosphate binding enzymes, but actually many important enzymes do bind those NTP. Same thing for NAD. Again, again, the same positions, 2' or 8, because those are best tolerated by most enzymes. And this brominated NAD mimics the natural coenzyme NAD and can be used for enzymes involved in the cellular redox cycles. Then the last piece is don't use single nucleotides, but incorporate the heavy atoms into oligos, and then use these oligonucleotides as ligands for enzymes that do bind oligos. So you can choose from our website. You can design your own oligo, and you can decide at which positions you want to use a brominated C, a brominated G, or a U. Or you can also incorporate an iodated C or U. So just order the sequence and you get the oligo ready-made. And this is of course only applicable for proteins or enzymes that bind DNA. But again, a lot of important enzymes bind DNA, such as transcription factors, methyltransferases and stuff like that. So in most cases they are crystallized in complex with DNA anyway. So, this is pretty much it. Manfred hasn't got up, so it's all fine. What's the take-home message for tonight, 9:47? There are more alternatives to just using tedious heavy atom screening. If you have to go for experimental phasing, meaning heavy atom derivatization of the protein or protein crystal. So before going into high throughput screening and try out all these toxic compounds, heavy atom compounds, mercury, platinum, whatever it is, there are these three examples of the clusters of the magic triangle or of the nucleoside derivatives that can be used. So their phasing power varies, So for the clusters and for the magic triangle, it's fairly high. For the bromine, it's a bit lower. So there's an estimate that you need about 1 molecule of selenium or bromine per approximately 100 amino acid for a proper MAD or SAD phasing. That's it. Just finally, I want to thank people who have been involved in this work. Some of them, you know, they're already here, Manuel and Sven, who have done some nice work on the clusters. Carsten, Tobias Beck, who we collaborate with on the magic triangle, Proteros, also involved in the clusters. And here are the people from Jena Bioscience, Christine and Thomas are here tonight, also at the bar, so they will be ready to take your questions, whatever you might have. And Larissa, she's not here, but anyway, she was involved in setting up this presentation. Thank you very much.
Thank you very much, also for picking very well in time. I suppose we have time for 1 or 2 questions, if there is any, and if you are not too impatient to go to the bar. Oh, there's a question.
Just wondering, for these tantalum and tungsten classes have mostly been instrumentally used for phasing big structures like ribosomes and so on and so forth. How applicable are they with smaller molecules?
They are thought to be especially useful when you have a low resolution data set only. So this is their major advantage. Don't ask me why, because I do not do any phasing experiments anymore myself. So, but size is not a problem.
But it was disturbing it couldn't actually bind because it was too big a thing, disturbing the context or something, but that's not the problem.
Yeah, I don't think that this is a general problem. Stuff like that, no binding or disruption or disturbance of the active site or this kind of artifacts, of course, can always happen with any heavy atom or any ligand. Yeah, sure.
Okay, I think with this I would like to close the session and thank all the 6 company representatives for their really insightful presentations.